Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from ByteDance Seed Lumine, a generalist real-time agent for 3D open worlds. Most modern AI models are excellent at reading and writing text, but they struggle when you drop them into a fast, complex world where they must see, think, and act in real time. Open world games are a perfect stress test. You have to navigate 3D space, understand visual scenes, plan multi-step missions, and precisely control keyboard and mouse. This paper asks a simple question: can we build an AI agent that plays these games end-to-end for hours at a time, with human-like efficiency? Lumen is the system introduced in this work. It's not just a model, but a full recipe for building generalist game agents. Lumen takes raw pixels from the screen and directly outputs keyboard and mouse actions, just like a human player. Inside, it combines visual understanding, language, and decision-making, so that perception, reasoning, and action are handled in a single, unified agent. Lumen is evaluated in Genshin Impact, a large 3D open-world game. It can complete the entire 5-hour Mondstadt main storyline at roughly human efficiency. Beyond scripted quests, it follows natural language instructions to perform a wide range of tasks: collecting items, fighting enemies, solving puzzles, talking to NPCs, and even operating 2D menus and interfaces. Perhaps most impressively, when you drop it into other games like Wuthering Waves or Honkai Star Rail, without any extra training, it can still complete long missions purely in zero-shot mode. Building such an agent is challenging for several reasons. First, open-world games are huge and open-ended. There's no fixed path, and the agent must constantly make navigation and combat decisions. Second, missions can last hours, so the agent needs to maintain coherent behavior over very long horizons. Third, it must act in real time, with tight latency budgets, or the game becomes unplayable. Finally, the agent must juggle low-level motor skills, like precise camera control, with high-level reasoning about quests and strategies. Under the hood, Lumen is built on top of a vision language model. Every second, it samples the game screen a few times, processes those images, and then generates a sequence of textual tokens that encode keyboard and mouse actions at a much higher frequency. These tokens are then translated into actual input events. Crucially, Lumen doesn't always stop to think. It uses a hybrid strategy. When the situation is routine, it directly outputs actions. When it encounters something complex or ambiguous, it switches into a reasoning mode, generates an internal chain of thought, and then resumes action generation. Compared with prior game agents, Lumen pushes several boundaries at once. Many earlier systems work in simplified or closed environments, or they only handle short episodes. Lumen is designed for fully open 3D worlds and hours-long missions. It's multimodal, jointly understanding visual scenes and language instructions. And instead of using a custom game API, it interacts through the same keyboard and mouse interface that human players use, making it more general and closer to real gameplay. The authors propose a 3-stage training recipe. In the first stage, they start from an open-source vision language model and train it on large-scale gameplay data that pairs images with human actions. This teaches the model basic control skills. In the second stage, they'd add natural language instructions, so the model learns to map instructions plus visual context into appropriate actions. In the final stage, they replace explicit instructions with internal thoughts, training the model to generate reasoning steps and then actions. This curriculum gradually turns a generic VLM into a capable instruction-following reasoning agent. To support this training pipeline, the team builds a substantial dataset. They begin with about 2,424 hours of gameplay, where screen recordings are synchronized with keyboard and mouse logs. Rule-based filters remove low-quality segments, yielding over 1,700 hours for pre-training. A smaller subset is manually annotated with instruction-level activities, which is then used to train a classifier that auto-labels the rest. GPT 4.1 helps refine instructions and captions, and a separate, carefully annotated set captures explicit reasoning traces. This layered process turns raw play sessions into structured data for pre-training, instruction following, and reasoning. A key innovation is Lumen's hybrid thinking mechanism. At each decision step, the model first outputs a special token that chooses between two modes. In thinking mode, it generates a chain of thought before producing actions. In direct action mode, it skips the thought and immediately outputs actions. This allows Lumen to reserve heavy reasoning for tricky situations like planning a multi-step puzzle while keeping most of its behavior fast and reactive. The result is a better balance between intelligence and real-time responsiveness. Because missions can last hours, Lumine can't keep the entire interaction history in memory. Instead, it uses a simple but effective context management strategy. It maintains a sliding window of recent image action pairs, along with a persistent system prompt and any accumulated reasoning. When the window fills up, the oldest visual context is discarded, but the high-level reasoning remains. Whenever the model generates fresh reasoning, the context is reset and rebuilt from that point. This gives Lumine a mix of short-term visual memory and longer-term strategic memory without overwhelming the model. To actually play in real time, Lumine must generate actions fast. The authors break down the latency across stages and aggressively optimize each part. They use tensor parallelism to spread computation across multiple GPUs, speculative decoding to reduce the number of full forward passes, and careful context management to keep sequences short. Combined, these techniques yield more than a 25-fold speedup compared to a naive implementation, bringing inference time down to a level that supports responsive control. To evaluate Lumine systematically, the authors build a benchmark of 141 tasks in Genshin Impact. These tasks span 4 categories: collecting items, combat encounters, interacting with NPCs, and solving puzzles. Within each category, there are simple tasks, harder ones, and unseen variants that differ from the training distribution. This setup lets them measure not only how well Lumine performs on familiar scenarios, but also how robustly it generalizes to new situations within the same game. The team also studies how performance scales with more training data. They train base models of different sizes on increasing amounts of Genshin gameplay, and track both training loss and benchmark success rates. As expected, more data consistently improves performance, but not all abilities improve at the same pace. Some skills, like basic navigation, saturate earlier, while more complex behaviors continue to benefit from additional demonstrations. This scaling analysis suggests that further data collection could keep pushing the frontier of what such agents can do. After instruction tuning, the Lumen Instruct model shows a clear jump in capability. On simple benchmark tasks across all 4 categories, it achieves success rates above 80%, significantly outperforming both its own base model and other baseline agents. This highlights how important it is to explicitly train the agent to follow natural language instructions, not just to mimic raw human actions. With instruction grounding, Lumen becomes much more reliable and controllable. When evaluated on unseen tasks, variants that differ from anything in the training data, Lumen's performance naturally drops compared to simple seen tasks. However, it still maintains a strong success rate, indicating that it has learned transferable skills rather than memorizing specific scenarios. The instruction-following version generalizes best, suggesting that grounding behavior in language helps the agent adapt to new goals and contexts within the same world. The authors explore how much historical visual context the model should keep. They vary the number of past frames preserved in the context and measure performance on the full benchmark. As expected, having some history helps the agent maintain continuity and handle multi-step tasks. But beyond a certain window length, the gains taper off while latency and memory costs grow. This highlights a practical trade-off: enough history to reason over short sequences, but not so much that inference becomes too slow. Lumine can be trained in 2 regimes, one that ignores past frames during training, and one that explicitly includes history. When evaluated, models trained with history tend to perform better on long horizon tasks, especially puzzles and multi-step missions that require remembering earlier states. Models trained without history still do well on short, simple tasks. This comparison shows that incorporating temporal context during training is important if we want agents that can handle truly long missions. The paper doesn't just report successes, it also digs into failures. By analyzing errors for both non-history and history-trained models, the authors identify recurring problems. These include getting stuck during navigation, mistiming combat abilities, and misinterpreting complex user interfaces. Long horizon reasoning, where the agent must remember and execute a plan over many steps, remains particularly difficult. This error breakdown helps pinpoint where future work should focus. One of the most striking results is cross-game generalization. Lumen is trained solely on Genshin Impact, yet when deployed in other games with different art styles and mechanics, it can still complete long missions without any fine-tuning. It handles a 100-minute mission in Wuthering Waves and the full 5-hour first chapter of Honkai Star Rail. This suggests that the agent has learned meta skills like 3D navigation combat patterns, and 2D GUI manipulation that transfer across very different virtual worlds. The authors are clear about Lumen's limitations. The training data, while large, is restricted to a single region of one game, and the reasoning dataset covers only about the first hour of gameplay. Memory is handled with a relatively simple mechanism, a short visual window plus stored reasoning. Learning is mostly offline from human demonstrations, so the agent doesn't yet surpass human performance through self-play or exploration. And even with heavy optimization, inference remains computationally expensive. These gaps point directly to future work in scaling data, improving memory, adding online reinforcement learning, and making inference more efficient. Stepping back, Lumine is important because it demonstrates a concrete, reproducible path from a generic vision language model to a capable, real-time game agent. With around 2,400 hours of gameplay data and a modest GPU budget, the authors transform a small, open-source model into an agent that can follow instructions, reason, and act for hours in complex 3D worlds. The strong zero-shot transfer to other games suggests that we're beginning to learn general-purpose decision skills, not just game-specific tricks. This has implications not only for research, but also for practical applications in game testing, AI assistance, and new forms of interactive entertainment. Finally, the authors address ethics. All gameplay data comes from consenting adult participants who are fairly compensated, and the work complies with the terms of service of the games involved. The system is explicitly not intended as a cheating tool or a way to gain unfair advantages in commercial games. Instead, the authors argue for open, collaborative discussion among researchers, developers, and players to design governance frameworks and safeguards. As agents like Lumine become more capable, that kind of dialogue will be essential to ensure they're used in ways that support creativity, fairness, and positive human-AI co-experiences.